Hi everyone. I think we're live. My dear guests, please come to the stage, turn your cameras on. And as usual, as every time, welcome to the whole world, ladies and gentlemen, dear friends and colleagues. This is the I-Core webinar number 10. Good morning, good evening, or good afternoon, depends on where you are in the world. And as it should be clear right now, that doesn't make any difference because we are the big community of scientists working in rehabilitation and assistive robotics all over the world. Again, as usual, my name is Claudio. I'll be hosting this webinar. Today we have three, again, as usual, prominent speakers, Marta Gandolla, Marta Gherardini, and Erik Scheme. Before I start introducing the guests, they will be talking about biosignals, the usage of biosignals. One of the big problems we have to control assistive devices. One little bit of advertisement. We, the I-Core, so the International Consortium on Rehabilitation Robotics, organize every 2 years the conference, the I-Core, the International Conference on Rehabilitation Robotics. Next edition, 2027, will be in Switzerland. Please keep an eye on the website, which will appear soon, and then come shake hands and interact. And speaking about interaction, this webinar is broadcast on the YouTube. You can field questions through the chat, and I will relay your questions to our guests. We are always on top of this, looking for organizers to these meetings. So if you think you have an interesting topic for the community and you can gather 2 or 3 speakers to do something like what we're doing right now, please drop a mail either to our beloved president, Dr. Robert Rina, or to myself, and we will guide you through the process. It is not difficult. You need to move your ass 2 months in advance, excuse my French, and then it'll be all right. So let me start by reading the biographies, the curriculum vitae that I received from our distinguished speakers. And indeed, Dr. Marta Gandolla, Politecnico di Milano, Italy, obtained her European PhD in bioengineering from the Politecnico in 2013. She carried out research activities at Politecnico di Milano, the University College London Institute of Neurology, and Fondazione Don Carlo Gnocchi, located in Rome, Italy. She currently is an associate professor in the Department of Mechanical Engineering at Politecnico di Milano. Her scientific work focuses on the mechanical and control design of exoskeletons, rehabilitative and assistive devices, experimental validation of said devices, and the development of technologies aimed at reducing the biomechanical load on workers' musculoskeletal systems. She actively collaborates with the WE Cobot laboratory and has contributed to technology transfer in the field of assistive robotics as co-inventor of 3 patents and co-founder of 2 startups called Agade and LER. She serves as an associate editor for the TNSRE, as myself actually, and the Transactions of Medical Robotics and Bionics. Our second speaker, Dr. Marta Gherardini, from the Scuola Superiore Sant'Anna, located in Pisa, again, Italy. It's a pretty Italian webinar today, right? So, Marta Gherardini is an assistant professor at the Biorobotics Institute of the Scuola Superiore Sant'Anna, where she conducts research in the area of artificial hands within the group led by Dr. Cipriani. We all know Christian Cipriani. She received her PhD in biorobotics in 2022, contributing to the ERC-funded project called MIKI, which led to the development and first-in-human validation of the Myokinetic interface, implantable magnets to measure muscle deformation for upper limb prosthetic control and sensory feedback. Her research lies at the intersection of robotics, biomedical engineering, and clinical translation, with focus on human-centered prosthetic technologies. She's involved in several national and international research projects exploring the usage of implantable magnets for the control of assistive devices, collaborating with clinical partners to advance innovative rehabilitation solutions. And now we have a double CV. So this is a joint work between Mr. Ethan Eddy, not yet PhD, so kudos. Actually, Mr. Eddy is a PhD student at the University of New Brunswick, Canada, located in Fredericton, a city I urge you all to visit, especially during the prominent conference called MEC, Myoelectric Control. Erik, next edition is next year, right? 27. Right, exactly. So even Eddy is conducting interdisciplinary research under the supervision of Erik and Dr. Scott Bateman. His work sits in the intersection of human-computer interaction, machine learning, and myoelectric control, with primary focus on improving usability and robustness of muscle-computer interfaces for assistive devices and general human-machine interaction. Today, his work is presented by his supervisor, Erik, Dr. Erik Scheme. So Erik received his PhD in electrical and computer engineering in 2013 from the University of New Brunswick, located again in Fredericton, Canada. And now he's a full professor of electrical and computer engineering, associate director of the Institute of Biomedical Engineering, and the director of MOBIL, the Movement and Biosignals Intelligence Lab, located at the University of New Brunswick. Dr. Scheme is an expert in myoelectric control and the application of machine learning in biomedical engineering, with research interests that span the broad areas of human-machine interaction, mobility and rehabilitation, digital health and diagnostics technology, and aging and biometric authentication. He likes to cooperate with people all over the world, I can testify that, and is interested always in creating meaningful opportunities for our next generation researchers through exchanges and collaboration, something that we could all subscribe to, actually. So I say, without much further ado now, I could call Marta Gandolla to the stage for our first presentation. You have 15 minutes, and as usual, I'm going to be as German as I can about the timing. Marta, the stage is yours.
Yes. So can you see the presentation correctly?
Yes, it's perfect. Thanks.
Okay, so thank you very much for the introduction. So I don't need to introduce myself again. So what I would like to start with today is about the needs, because this is something that we all start from, right? So I would like to start with this quote from a scientific paper, but is directly from the mouth of one of our patients. So from the patient's point of view, improvement is measured by regaining lost abilities, by being able to do anything today I couldn't do yesterday. So sometimes we just don't get really what they would like from us. So the first thing that we did for the project that I will present to you today is that there will a pool of persons from WILD, which is the Italian Association for the Fight to Muscular Dystrophy. And they came to our lab, and we asked them, if you would be able to move your arm again with the help of the technology, what would you like to do? So we made a broad question, like, sort of, and those are the answers that we get from this interview. And there are some things that might be something that we could imagine. So, for example, reach a point of a table, for example, the mouse to work, or return the arm to the wheelchair, or to control some automation devices. But also, for example, just move the arm per se to counteract pain caused by prolonged posture, which is something that we don't think about, but they do stay the same position. And also something like that was surprising a little bit, there was, for example, to play chess. Of course, depending on the residual of the end, but these kind of patients have the muscular weakness that starts from the proximal part of the arm and arrives to the end. So they have a situation where they cannot move the arm against gravity or at all, but they still have some dexterity at the end level. Okay, so the idea, so we had those many requirements, functional requirements, let's say, from our patients. And so the idea was to develop a fully motorized upper limb exoskeleton, because they don't have any residual function in the upper part of the limb, capable of assisting movements at shoulder and elbow while leaving the hand unassisted, but that was directly and continuously under the control of the patient itself, or herself or himself, to be able for them to select and to choose what to do with their arm. So this is our our exoskeleton. This is the CAD, and this is the realization of the exoskeleton. So you can see that we have 5 degrees of freedom. One that is the 3 at the shoulder, so the 3 main at the shoulder, so shoulder abduction, adduction, flexion, extension, and humeral rotation. And then we have elbow flexion, extension, and then the assistance for forearm pronation, supination. But now let's go to the topic, right? So we have those motors. How do we get biosignals to control this assistive device? And so we came up with those 3 options. One is manual control, vocal control, or gaze control. So as per manual control, we have this joystick that is a 2D joystick with a button. So you move in the plane, in the horizontal plane, then you press the button and you go up and down. So you can see on the right-hand side the graphs. You can see that before you move in the XY plane, and then around 3 seconds, you press the button and you move in the Z plane. And here we did the evaluation of those three ways to detect intention detection with 3 subjects that you can see listed there. We asked them to fulfill the SUS, so the system usability scale, only about the use of the interface. And we can see that the joystick, so the manual user interface, is quite well usable. And the first, we can see here, the first subject selected the manual control as the best one. Then we go on the second one. I'm sorry, that's in Italian. I don't know if you can hear. But basically what happens is that we have some hot words that can be recalled by the person. Of course, here they are in Italian because we developed with an Italian pool of patients, and we had to see and to verify that the hot words that we have selected were recognized, particularly because our patients do have sometimes the vent, as we can see in the video here, or they have some difficulty maybe to talk. So we had to verify if the hot words we recognize were effective. And we can see that the usability, again, here in the table, we can see that the usability is very good, also for the vocal user interface. And the other 2 subjects here, they selected the vocal user interface as the best one. Then we go to the last one. This one is the gaze control. So basically what we had is to have a table mounted eye tracking system where we have basically implemented the virtual joystick. So you can see, what we can see now is the calibration of the device, which is very easy and very fast. And then you start your application, and you can see that we have these buttons, and you can use the eye tracker or the gaze control to control the position, the effector position, as with a joystick. So go left, right, you want to go there, and so on and so forth. We evaluated the fixation detection error for our subjects, and we saw that it was definitely usable. Indeed, here the results of the system usability scale for the gaze control was excellent as well. But actually, and this is something that I really want to share with you. So it was usable, it was effective, it was good to drive our exoskeleton, but the patient said that though it was usable, they didn't want to use it, because they said, if I am able to move back my arm, since many years I don't move it anymore, I want to look at my arm and I don't want to look to a screen. So this is a take-home message that I want to share with you, that sometimes we develop stuff that works, maybe that they ask for it, but then it is not what is useful in their daily life. So this is something that we need to assess also. Then the way the assistive device works is quite easy. So we get the input so now from the manual user interface or the vocal user interface, and then we generate a trajectory at the end effector level. So we have a displacement in any of the X, Y, or Z direction, and then we compute the inverse kinematic to control the velocity of each single joint to perform the movement accordingly. Then what we did is, beside the pilot study that we've done with the 3 subjects that I showed you before, we did a usability study with 14 participants. Basically what we did is we had two assessment points. So with the use of the device and without the use of the device, and they have familiarization with the device in the middle to use the device as assistance. Okay, and we evaluate the pull scale, which is the performance of upper limb scale, the Abilan scale, which is the assessment of the upper limb, but not from the clinician point of view, but is a self-reported ability of the upper limb, so is performed by the person. And then the system usability scale. Of course, the system usability scale is only performed on the device. Then here you can see that our first result is definitely that the system usability scale was excellent, even though it was a prototype. So it was a single prototype. You can see that the activities that they've done are various activities assisting what they need to do in their daily life. Here I want to show you the results, and I would like you to show the results for the pull scale. So just as I recall, this is the performance of upper limb scale, and it's about the evaluation given by the therapist to the person. And we have the gray scale without the help of the exoskeleton, and the greenish scales with the help of the exoskeleton. And you can see that all of them, all of the person has improved in terms of functionality of the upper limb with the use of the exoskeleton. I just want you to please note the first person here, participant 1, that do increase the ability with the exoskeleton, because then we will comment afterwards. And I just want to mention that the minimum detectable change or meaningful change in this scale is 4 points. So they all meaningfully improve their functionality. This is the Abilan scale. So as I mentioned before, this is a self-reporting scale. So basically you ask to the person how easy, difficult, impossible do you feel that this action is for you without having the exoskeleton and with the exoskeleton. And what we can see is that all of them perceive the exoskeleton as an help for their activities of daily living, but for the first patient, okay? So we can see here that this one perceived the exoskeleton as a limitation, even though it is not true from a clinical point of view. And this is because the exoskeleton, even if it helps you out in performing more activities than before, it constrains some of your counteracting movement that you made in place to counteract the disability. Okay, so it can be felt as constraining a little bit the movement as you are usually doing them. The other thing is that the possibility to move back the arm is perceived as very game changer for some of the patients, even if this is not really possible, but they perceive that the exoskeleton could help them a lot. Okay, so that's my my last slide, because of course, as everyone, I would say this work is the result of a big team of people working on that. So first of all, my colleagues, of course, the patients, the volunteers that came for the study, and all the funding agency that helped us. And also, I would like to mention that we have a new version, similar, going to the product version. And so, if you want to collaborate on that, of course, we will be happy to do that and to receive your help and your contribution.
Thank you very much, Marta. Sharp on time, even shorter than expected. So big novelty. Good. Marta, would you like to jump on stage then?
Yes.
Thank you very much.
Can you see my slides?
Coming right up. Yes, it works. Thanks.
Okay, thank you. Thank you for inviting me. I'm really glad to be here today to talk about our research. So, as I'm part of the Artificial Hands Laboratory, of course, our main topic is hyperlimb prosthesis. And in the last years, there have been a lot of devices that have been released on the market. I'm talking about anthropomorphic hands that are capable of very complex movement and high dexterity. So while there are a lot of options in this sense for the users, the great challenge of the field remains how do we achieve natural control and sensory feedback, and which biosignals do we use for that? Regarding this, in the last years, there has been a lot of research to discover which is the ideal human-machine interface to achieve these scopes. So both for connecting with the sources of control, so basically the muscles, and also how to restore sensory feedback in a natural way. And there has been a lot of advances in two fields. So basically in surgery, where there has been the development of novel surgical techniques, for example, targeted muscle reinnervation, LPNIs, that have allowed the reconstruction, in a sense, of the missing limb and the creation of novel control sources. On the other hand, novel probing and stimulating technologies, for example, implantable EMG sensors or implantable neural sensors that have allowed to probe the signal directly at the control source, at the biological control source. In this scenario, what we proposed was a different paradigm that instead of exploiting as is usually done, the electrical signal of the muscle to control and the electrical stimulation for providing sensory feedback, exploited instead the deformation that muscle undergo following contraction, and does that by using implantable elements, which are the implantable magnets. The idea of exploiting deformation for prosthetic control is actually not novel. Already in the end of the 19th century, cineplasty were proposed, in which basically the tendon or the residual anatomy was directly connected to the prosthesis to actuate it. Of course, it was a really invasive surgery, but also the first case in which proprioception was naturally restored during prosthetic control. More recently, although, however, there has been a switch into more biomechanical-based control, still based on muscle movement, muscle deformation, which exploits some technologies, different kind of technologies, like, for example, sonomyography, which is based on ultrasound, or force myography, which is based on the use of force sensors. And in this scenario, we include also the Myokinetic interface, which is the only one based on implantable elements. So the idea is that you insert surgically a permanent magnet inside the muscle. This will generate a magnetic field that will be sensed by external electronics, so basically all effect sensors. And this field will vary depending on the magnet position in real time. So what we did was implementing a numerical approximation-based algorithm that tries to match the measured field with the one modeled through the magnetic dipole in order to reconstruct the position of the magnets in real time. And what you see in this slide is actually the results of this algorithm. So the algorithm is implemented on a single computation unit that collects the data from all the sensors that are the green border that you see in the image, and then reconstructs in real time the position of one or multiple magnets implanted in the muscle. For example, in this demonstrator, you see 8 magnets that are moved simultaneously by a mock-up, which simulates muscle contraction. And the video on the bottom displays the movement of these magnets in real time. The system works in real time, so 8 moving magnets simultaneously, which is kind of the worst case for us, requires around 60 milliseconds for position and orientation reconstruction. We first tested this system in a non-invasive way, so as a preliminary study that we conducted together with the Medical University of Vienna, the research group of Professor Assmann. We recruited 2 patients that previously underwent targeted muscle reinnervation, and we tried to understand if it was actually possible to classify different grasps, different hand and limb movements based on the displacement of the muscles. And to do that, we carried out some video analysis represented on the left, and then replicated the same experiments by applying magnets on the skin as represented on the right, and asked the participant to perform different grasps and recorded the movement of the muscle that we could see from the surface. We recruited targeted muscle reinnervated patients because actually you can see really a lot of movement when they contract the reinnervated muscles. And this is the result. So on the left, you see an example of line classification that we did afterwards through the video analysis, in which you can see that we were actually able to retrieve the grasp that the person wanted to do based on the deformation. And the graph on the right shows the results both for video analysis and for magnet. We applied, of course, pattern recognition algorithms. So what you see here is the accuracy. And the results demonstrated that it was actually possible to exploit deformation to classify grasps. Naturally, the next step was to go invasively. So we did the first implant and the first realization of a cell-contained myokinetic prosthesis in 2023 in the hospital of Pisa. So this participant received the implantation of 6 magnets. 2 of them you maybe are not seen in this video because they are behind the bone, but they were 6 magnets implanted in 3 different muscles of the forearm. And we realized this custom prosthesis in which the socket embedded all the electronic parts, so the sensor acquisition boards and the computation unit and the battery. So in the end, the only implantable parts were the magnets, which of course were previously coated with a biocompatible material in order to make them compatible for in-body application. So this first trial lasted only 6 weeks, so it was a temporary implantation, being a pilot study and a first demonstration. But still, during this short time, the participant was able to use the prosthesis controlled with the magnets, as you can see from this video, and perform activities of daily living, functional tasks. And in the end, results show that the functionality that he was able to achieve was comparable to that of current gold standard, if you want, which is myoelectric control. At the same time, I mentioned previously sensory feedback because the myokinetic interface actually has the potential of being used in both directions. So both to restore control, but in another way also of restoring sensory feedback by exploiting the concept of proprioception. So proprioception is the ability of being aware of where our body is in space without looking at it. And the previous studies demonstrated that by providing 90 Hz vibration at tendons or muscles, there is the possibility to give the person an illusion of movement of that joint. So, for example, if I provide vibration to the biceps, the person can have the illusion that the elbow is extending. So we thought, why not exploiting the fact that we have magnets inside the muscle near to these receptors, and we could provide vibration in order to activate this receptor and restore proprioceptive sensation in the user. For the first time, having a technology that allowed us to decouple the cutaneous perception, because generally these vibrations are provided through vibrators applied on the skin. In this case, we decouple it from proprioception felt from deep inside the muscle. So we developed this technology that uses external coils to selectively vibrate one magnet or multiple magnets and selectively keeping still other magnets, and is capable of simultaneously localizing magnet position and stimulating them in order to update the torque needed for vibration based on the current magnet position. And we actually tried that during the first clinical trial. So what you see in this video is an ultrasound recording of the participant and in particular of the implanted magnets, which is the white disc that you see in the video. So we did some perceptive studies in which we tried different frequencies, different amplitudes of the vibration. And in the end, the participant actually reported that they could feel coordinated finger movements of closing and opening during this vibration, and at the frequency which we expected. Results of this study are currently under review, and hopefully they will be available soon. So what now? After this first temporary study, what are we doing now? We want to, first of all, extend the duration of the implant. So what we did in the last 2 years was mainly working on finding a new coating solution that would make the coating more resistant in order to allow us to conduct a longer clinical trial. And also we are focusing on optimizing the surgical procedure for implantation by creating a sort of planning and guidance system for the surgeon, because in having an optimal surgical realization of the interface is essential, is crucial in order to have a proper signal-to-noise ratio of the control signal, and so a correct functioning. On the other side, we are also exploring the possibility of extending the use of the same interface to for the control of other types of assistive devices. So, for example, we are working on a project in which we want to apply the Myokinetic interface to the control of lower limb prosthesis, in particular targeting the transtibial amputees who underwent the AMI surgery that basically reconnects agonist and antagonist muscles. So we started by carrying out some FEM simulations to understand how those muscles would work after undergoing the AMI, what contraction we should expect. We developed also some kind of mock-up, as you see in this picture, so a physical system in which we try to recreate the movement of the magnets due to ankle movements in order to develop control strategies that then we would like to test in clinical trials that will be done in Italy, are planned to be done in Italy. So the idea is to control active robotic ankles in collaboration with Istituto Italiano di Tecnologia and Scuola Superiore Sant'Anna. The other research line instead focuses on extending the myokinetic interface to the control of exoskeletons, so wearable devices. And in this case, the interesting fact is that we changed the design of the system. So the one you have seen before in prosthetics is based on a single microcontroller that localizes all implanted magnets. And this requires a rigid anchoring system, for example, a socket that embeds all the electronics, and so that the relative position between the sensor boards stay fixed during all use. Instead, to make the system more adaptable and compatible also with wearable devices like exoskeleton that don't present a rigid anchoring system, we developed this system which is based on multiple independent localizer and flexible PCBs. So basically all PCB are flexible, can be adapted to the shape of the arm, for example, or the body district in general, and every single board implements its own localization algorithm. So that basically we are able to independently localize different magnets implanted in different parts of the body, and we don't need any rigid anchoring system to hold the sensor boards. I'm skipping the last slide because I'm guessing that I am a bit late, but if you have any questions, I will be happy to answer them later, and thank you very much.
Just great, Marta, thank you very much. Remarkable talk. And well, it's time for our third speaker. Erik, the stage is yours.
Great, thank you very much. Both very interesting talks. Thanks for sharing those for sure.
Oh, yeah.
Let's see. Okay, are we set up? Can you see my slides?
Actually, no, you're not sharing.
No.
I have to hit the second button. Yes.
Yeah.
It's the Zoom thing.
All right, good.
Excellent. Okay, thank you very much. I want to say thank you to our first speaker who particularly helped set up some of what I want to talk about today, and both for very interesting talks, of course. And so the work I'm going to present today is largely the work of Ethan Eddy, but also Evan Campbell. And I would have hoped they would have had this opportunity, but Ethan wasn't able to make it today. So although a lot of our work is most known for continuous myoelectric control for prosthetics, today I'm going to talk about something slightly different, what we're calling discrete muscle control interfaces, potentially for uses in assistive technologies. And so as we saw today already, there are many different inputs for assistive devices, technologies. Some of them work well in some situations. Sometimes people don't want them the way they work. Obviously, voice plays a good role, but there are also limitations in terms of when people may want to use that. Computer vision is often being used for things like virtual reality right now, but requires a lot of dexterity, and access to cameras and buttons and switches can be limiting at times. And so I want to bring us back to this idea of muscle control interfaces, which is really just myoelectric control, but we're branding it slightly differently. I will note there is some gratuitous use of AI images like the one on the right that you see here, just for effect in the presentation. I recognize those by Nano Banana 2, which is the tool I use to make them. But the idea of using EMG signals to recognize the underlying intent of the individual could be used as input for assistive technologies. And the question is, why aren't we using these more? You heard a lot of talks today about sort of other things other than EMG, and particularly when we talk about assistive devices, one of the issues is that EMG signals vary significantly between users. For a long time, that was sort of the assumption, was that every model had to be user specific. We also know that EMG signals vary significantly across sessions, and so this could be due to confounding factors like limb movement or electrode shift or just behavioral changes over days. But for this talk, I'm also going to argue that we've historically relied too much on prosthesis control strategies just because they've been the dominant application of myoelectric control for a long time. And that may not be the best approach when we're applying to use some of these other technologies. And so the term discrete muscle control interfaces, I'll differentiate here. Some people will probably think of discrete EMG as classification, where you're breaking things up into classes rather than a continuous regression. The way that we're using the term discrete here is actually more in terms of a sequence of actions that then gets mapped to a specific discrete output. So think of finger snap like that. This is a continuous temporal trajectory that then gets mapped to a discrete output that could be used for things like swipes, taps, or discrete inputs like buttons in assistive devices. And it turns out when we do that, we actually get quite a bit of power that we don't get in the continuous control schemes that we see in prosthetics. And so the idea here, again, we see the model gets trained on an entire template, a gesture template of movement. In this case, a specific example of using temporal models, LSTMs, to sort of learn the temporal patterns and then combining those into an output. And then the prediction gets made after the sequence is detected, rather than every single 60 milliseconds or whatever increment rate that we often do in prosthetics. And and so if we think about it that way, a lot of emerging technologies are actually interacted with that way, whether it's gaming, so quick button pushes or interfaces, whether it's interacting with smart homes to turn on a TV or change channels or enable a light, or shared control systems where we might not want to do continuous control of a device, but allow the device to have some of the local closed loop control, but still be able to intermittently interact with it. So for example, go forward until I tell you to stop. And so it comes back to, okay, well, if we can make these things work, what are the issues? And the issue is that these muscle control interfaces have historically been limited to user-independent models that require frequent calibration to remain the robustness or maintain that robustness. But particularly as we move towards maybe more consumer applications or more sort of convenient applications that aren't in the prosthetic space, we particularly want these things to have little to no calibration, just as we did in prosthetics. And so the question is, can we achieve these discrete muscle-computer interfaces that maintain robustness without the need for this frequent or potentially even any recalibration? And so one of the things that got us going in this direction was a database that was collected in Ecuador. I think this group has made a significant contribution to the field. They used the Myo armband to collect data from 612 people doing a series of different gestures. Nothing particularly fancy about the protocol, just asking people to repeat these contractions multiple different times. And so we've been able to leverage this data set to large effect because it's one of the first times that we've actually seen as a field a large data set of EMG that could really start to leverage what we can do with these machine learning models now. And so if you look at some of the results that we get coming of that, we're actually seeing models that are getting 93% accuracy on these discrete gestures. So again, this is different than the continuous control case. This is 93 out of 100 times perfectly recognizing the action of the user in a discrete movement. And what this plot represents is zero-shot performance on a completely new user that was not seen by the training of the model. And so what that means is we train a model with 300 users, that is a byproduct of the way the data set is broken up. And then we just put it on the new user or test it on a completely unseen user, and we're getting that 93% performance out of the box. But if we compare that to what we see in a number of EMG studies, we're typically, that 10 to 20 range, and we see that the model is down to 80%, although that's still 80% zero shot to completely new users. So part of what we're seeing is the leveraging of the temporal profile of that discrete gesture helping in the generalization across users, but we're also seeing a lot of benefit from adding just more users to the model. And you can see a latent space t-SNE projection here that we're seeing very good separation of the data, even though it's all completely different subjects in the model. And it turns out not only do we get pretty good cross-user performance with no new calibration on the end user, we actually get much more robustness built into these models. And so we've been playing with a few things where we sort of collect some of our own data. So this is data trained with that large model from the 300 or the 612 users, and then applying it to completely new people wearing the Myo armband, in some ways multiple years later, in a different country. And we're seeing good resilience across days, but we're also seeing quite good resilience across things like limb position, which we know has degraded myoelectric control fairly substantially in the literature. So not only are we getting some benefits of sort of reduced training time for the end users, we're actually getting increased robustness by being able to take advantage of these things. And so the question is, do these discrete offline models work in generalized online use? Because those results were sort of just using data that we collected in a similar way using offline data. And what's interesting about online discrete controls, it's slightly different than the continuous modulation of a prosthesis based on proportional control and nudging the prosthesis. Again, we're thinking more discrete inputs. And so what we did here is we took those models and then we created sort of an interactive environment where we asked users to respond to prompts. So you can think of this as dismissing a phone call or reacting to something in a game where you're asked to elicit a particular class in response to that input. And what we saw here is actually we're on par without training on the end user, we're actually on par with a keyboard input type response. This is 5 different classes of motion. So 5 different keyboard keys versus 5 different EMG classes. And we're seeing response time pretty much on par with keyboards, but we're also seeing very, very, very low error rates in this particular case as well. And so we see on the first and second error rates bumping down to medians of 0 time. And we have very few false activations in this case. Turns out to get this performance, one of the things that we did in the lab was we augmented the data set that we got from EPN, but we added data of our own to the model. And specifically what we did was we collected data from users that were doing, we'll call activities of daily living to expand the no motion class. So one of the things we're really looking for here is not only good performance when we want it, but also to be able to acquiesce unintended activations, particularly if people have use of their hands to do other things. So we augmented the no motion class in this case with people doing finger wiggling, they were walking, sometimes they were writing or typing on a keyboard using a phone. We took all of that data and embedded that in what's known as the no motion class for this to be able to build the model resilience to say, those are not inputs that I really want to respond to. I only want to respond to those 5 trained inputs that I've trained the system on. So I think there's a lot of promise there. Now, one caveat of that work so far is that it has been largely, it's been done with healthy subjects, able-bodied subjects. And so the data in that repository is likely not fully representative of the assistive technologies use case, of course. And so we do need to sort of consider, okay, not always are we going to be able to build these great cross-user models and then just put them onto somebody directly. And so we've been starting to work a little bit on understanding how do we actually adapt these models. We want the best possible baseline model so that these work as well as possible, as robustly as possible, but retain the ability to fine-tune it for an end user. And so, again, this particular result is with able-bodied subjects, but it turns out if you add a little bit more data from the end user, we can take that 93 baseline and drive it up substantially by adding user from the more data from that end user. And so there's a couple things happening in the model in this case. It is adding representative examples for the end user, but we're also fine-tuning the weights of these networks to learn the specifics for that user. So we see a lot of benefit. We're seeing additional benefit in using contrastive learning for this, for those that are aware of those kinds of things. Now, we still understand that adding training data, the way we've typically been doing with the screen-guided training-based approach, is limited. And so this particular figure comes from Evan Campbell's doctoral work looking at continuous control. But what he's been able to show pretty effectively is that user behaviors as seen during training, which are colored here as the different colored dots in this plot, is not representative of the actual patterns that people make when they're trying to control a device to do something. And that's all those black dots here. And so there has to be an acknowledgement that the way we train these models needs to be reflective of that use. Certainly, we could build much larger repositories and data sets of variable data, but we also need to be able to adapt these models to the end user. And so Evan's work's been focused on what he's calling context-informed incremental learning. And the idea being here that we have an agent operating in an environment. Unsupervised adaptation models would typically just use the output of the model itself to try to adapt itself. However, that's fraught, particularly if that model is not working well. And so we've been leveraging context from the environment, saying not only what did you mean to do, but did that make sense in the context of the task that you're trying to work on? Reinforcement learning does something similar. However, it's so sparse in terms of rewards when a user is in the loop that can be frustrating and take a long time to get up and running. So CIL is kind of a happy middle ground where we're leveraging goal-oriented behaviors, but leveraging context from the environment to still inform supervised learning so that things can adapt quite quickly. And it turns out when you do that, we're seeing significant improvements with large effect size. And so this is a work that's in submission right now. And there are multiple different numbers on this screen, but I'll refer you to sort of the top one, the MLP static. This is a neural network trained with typical screen-guided training. And what we see on the top right is if we have large targets, as we'd normally see in a Fitts law style target acquisition task, we get a performance of about a bit per second in terms of throughput. And we see with Evan's latest model, we're almost at 2 bits per second. What's maybe more exciting is when we reduce the size of those targets to very small, where the traditional models have a hard time stopping exactly where they want, the models are still retaining a lot of their strong performance. So this is really exciting. We're also seeing the plot on the right that the more you use the models and adapt to it, users are adapting to lighter and lighter contractions to achieve that even better throughput. And so we're continuing to work in this space. The good thing is that it's not limited to only continuous control. And so in this idea of discrete inputs, we can also leverage CIL, particularly if you're using digital interfaces where you have ideas of the context. We can leverage that quite nicely. And so that's our ongoing work right now, is trying to figure out how can we not only adapt these discrete models to the end user, but continue to adapt them over time so they can continue to get better and better and better. It's actually a little bit easier to instrument for discrete control. However, the rewards again become a little bit more sparse because you have fewer inputs. It's not a continuous decision stream. So that's ongoing work. So some summary and key takeaways here. We really are excited about these sort of discrete muscle-computer interfaces for assistive technologies. We're going in the direction of understanding how they can be used, whether as discrete inputs for mode switching or specific devices. They also could be paired very nicely with shared control systems, as I said, about reducing the burden on the user by sharing some of the autonomous control with the devices themselves. And they can be complementary for other assistive inputs as well. We saw our first speaker talking about gaze tracking. You could actually pair discrete muscle computer interfaces to do faster selection of inputs or things like that. And we're seeing again that these are possible. We're getting better resilience to real world factors, but there's still work to be doing on personalization adaptation. See Claudio jumping in. I'm just going to say these are now being integrated into our open libEMG library that is open and around the world. So if you're interested in playing with EMG as inputs or outputs for different devices, feel free to check out libEMG. Otherwise, thank you very much.
Just great, Erik. Thank you very much. Great talk. Great talks, all of you, I have to say. I'm really enjoying this. So I think we go 15 to 20 minutes in which we can open the floor and throw in some more food for thought. I actually have one question for each one of you, and then we might start cross-interrogating one another or maybe comment on general issues. So I'll start with Marta Gandolla. The kind of signals you guys are using in Milano, I see them as posing a certain cognitive burden on the user. So joystick, vocal control, and gaze. I'm especially interested in this remark that you got from one of your patients, right? So yeah, gaze is fine, but I'd like to look somewhere else sometimes. So I'm appreciating a lot your study of the usability and acceptance of the different kinds of inputs that you have. Can you comment a little on that? Or do you have any perspective on this? So what would be your ideal interface if you could have it?
Good question. Who knows? No, yes, this was something that we learned a lot from this study, but I think that is the experience from for anyone that is working really then with patients and with assistive devices. The cognitive burden on the gaze, there was a little bit of cognitive burden, but for the joystick, actually, we might think that is difficult, but they use it as interface with their normal life all the time, because, for example, they have electric wheelchairs. So I think that the point is there to exploit some interfaces that they already are used to have in their daily life. So we all, no, maybe not all, but many of us as a Siri or vocal assistant, as Alexa or things like that. And so it's something that we are usually using for leisure, for other stuff, but that we can exploit for assistive devices, same for joystick, for these particular patients. I think that the point is to find something that is, so since it becomes part a little bit of their life, like, for example, the smartphone became part of our life a little bit. So the point is to exploit something that is part, that they perceive as part, an extension of their body, and is part already of their life, if possible. Of course, the other direction, and this for more standard maybe interfaces. Of course, if we look at implantable devices, for example, for EMG, as my other colleagues maybe can comment on that. So we are using them, the EMG, for example, as well, but they can comment on this. I think that the challenge there is to use them in a seamless way with respect to the person. So not teaching them how to interact with magnets or with EMG, or to deliver a specific muscle contraction, but there the challenge is to get signals that are already there and use them in a meaningful way. I think that those are the two challenges, but maybe Marta and Erik can comment on.
Actually, comment on very quickly on this. You pointed the finger at one of the open wounds here. So we engineers, we're all engineers, right? I will never get tired of repeating this. We like to build our own toy, and we're so proud of our ideas. Then you ask your patients, what's wrong here? Or what could I do better? Or what am I doing wrong? And you always get answers that we were not expecting, because as long as you stay in your lab, you cannot possibly know. Do our speakers want to comment on this, on Marta's remark?
Yeah, that's a good question. Marta, go ahead.
You go. No problem.
Okay, we call that a Canadian standoff here. Yeah. So yeah, I mean, obviously, if we're trying to build devices that are going to be helping end users, we need their voice. We need their voice at the table for sure, right? And so it becomes a little bit of a catch-22, or at least, as you say, Claudio, as engineers, we convince ourselves it is, that we need to get it to a point where it's at least close enough where we can give an idea of what's possible. But at the same time, we need to be co-developing that with end users so that we're not going off in a completely wrong direction, right? So, I mean, I think that's true for anybody in this field of biomedical engineering. I mean, if we want something that's going to work, we need to speak with the people who are going to benefit from it.
Co-design is this keyword is on the go in our community right now. It's very popular.
Yeah.
Yeah, I totally agree, both regarding the need, of course, to speak with the end users. This is really important, both in the design and also then in the testing part. When you work with implantables, sometimes it's more difficult because you have a smaller group of participants generally with which you can interact, and you spend a lot of, for us, it's difficult sometimes because we spend a lot of development years in which we don't have the possibility to really test the technology. For example, in these periods of development, what is really important is also the contact with the clinical partners. So I mentioned also in the presentation that we are engaging with them also regarding the surgical procedure planning, execution, because sometimes this is this is not evaluated in the starting phase, let's say, of the development, in which you are focused on the technology to work well and to develop your prototype. But then you work together with the clinicians, especially with implantables. So it's really important to engage both with them and the end users. And also to answer Marta's point regarding implantable technologies, I agree. And indeed, the idea, at least for us, was to exploit physiological signals, meaning the signal that were actually used, for example, to move a finger, to use the exact same signal to reproduce then the movement in the prosthesis, because one of the advantages of going invasive and taking the signal selectively from a biological source would be to exploit exactly the same signal for the same action. So this is the target, of course, and it could be the advantage of implantable technologies.
Yeah, I believe, yeah, minimally invasive technologies such as yours should provide more accurate signals than surface. This is as opposed to that, you have to be minimally invasive. By the way, Marta, I have a, slightly more technical question for you from the YouTube chat, but given that your technology is possibly the most experimental one we've seen today, it makes sense. Lucas Fonseca is asking, can the magnets move to a different location over time? And or how are they anchored? I believe he means how are they anchored inside the muscles? Of course, I guess if they shifted freely, then after a while you should have to recalibrate the entire system.
Yeah, exactly. So this is actually a good question. So the problem is migration. So we asked ourselves also in the first place, will the magnet migrate once they are inserted surgically inside the muscle? So actually the answer in general is no, because what happens is that there is a fibrotic reaction of the tissue that after some days create a sort of capsule around the implanted element that hinder the movement. So the magnet will not migrate around. What we did in the surgical implementation was to use some surgical glue that was reabsorbed, just to make sure that in the first days it didn't go around, but then we didn't notice any migration, and it was also not noticed by other research groups that are investigating similar technologies. The only thing you need to pay attention actually is to maintain a minimum distance between the magnets when you implant them because of the magnetic attraction. So you need to be safe. There is a distance threshold that we calculated based on on the magnets that we use that you need to maintain to make sure that they don't attract themselves. In that case, it was also proved that migration would occur.
So they sort of get into a cyst after a while, and then the cyst is implanted, is anchored to the muscle, so they cannot really move relatively to the muscles.
Exactly, yeah, that's what I mean. At least surgeon explained to us like that. So yes.
This is great. This is great. Thank you very much. Well, Erik, a question for you. We're sort of working together on the CIL project, so I love the way this is a way to keeping the user inside the picture. So having the user play a role, an active role into the data gathering and improving of quality. Speaking about which, yeah, I mean, can you comment a little on that? So do we plan to have some way of checking the change in the data quality across sessions or something like that, I guess?
Yeah, so the CIL is quite interesting, and we're pretty excited about it. It's a simple idea, the idea of adapting the model with the user in the loop. There's been lots of research about how to do that and maintain stability. The real thing is being able to capture goal-oriented behaviors with labels for those, right? So in the past, we've said, well, we could get the data, but we don't really know what the person was trying to do. And so if they're doing something that the model wasn't really familiar with, machine learning is just going to put a label on it and move forward. And so leveraging that context really changes things. And why I think we're really excited about it, beyond the idea that you can build better models, is that it's personalized models. And so, for example, if you put somebody in an environment and say, I want you to, in a game, go to the right, say, for example, and my bias is to say, for me, that is to extend my wrist to go to the right. Over time, if that person changes the way they do it, or they do it slightly differently, or they decide that some other pattern is better for them, they can just do that. And the model, because of the context in the environment, will learn, oh, actually, this is how I want to do it. And potentially it can learn multiple different ways to execute the same action as well. So like I said, we were a little bit surprised to see that the model actually was adapting to lower intensity contractions. I think that's been a challenge in the field of myoelectric control, that we tend to just kind of do really hard contractions so they're differentiable. And I think that's a sign that the users are saying, I trust the system more and more as I go. So I'm going to go to lighter contractions, which in the end should be a better thing.
I would just mention shameless advertisement. We have a paper out which is about exactly incremental learning, which means you have something which will need to gather more data from the user as time goes by, whenever it is required. And I see CIL as one of the best ways for the system to actually attach the right label to the data that the user is producing. And this is a general approach. So it regards all the approaches that we've seen today, and basically any approach based on machine learning.
Yeah, it's not EMG specific at all. I mean,
Exactly.
we could do it with the magnets. We could do it with any of the other inputs as well.
You can do it with gaze tracking. You can do it with, but even the way you use a joystick might change in time. So in the end,
Correct.
good. Does anyone have any general remark here? So we still do have a few minutes to maybe throw on the plate some general issues. I mean, I have in my heart the issue of reliability, but that's something that you need to test in the large. So rather than in the large on many people, possibly even on fewer people, but on longer times. And then in the end, when people are satisfied, then we know that reliability is achieved. Is there any other ideas that you need to discuss here, or issues that you think we're still facing in general when using, and this brings me back to the general topic of this webinar, using biosignals, so trying to understand what our users want our machines to do. What's the big issue here, in your opinion? Marta Gandolla, sorry for using your surname again. We need to
And
do
of course,
that.
ladies first.
First.
Marta's Gandolla's first.
We are old-fashioned people from an old continent, always.
I think that one of the challenges that might be interesting for all of us is multimodal intention detection. So what we do, how do we interact with the environment is multimodal. So we don't use a single channel to interact. Neither. So as we were speaking as Italians, we use the voice, we use the face, we use the hands, we use many channels of communications. So I think that one of the challenges might be multimodal intention detection to reach the same task, but maybe to modulate it differently. So a bit what Erik was discussing before, using different strategies to reach the same task, different strategies, and also different channels of communication with the environment. I think this might be a great challenge, and we can team up, right? From different teams to do that.
This would be great. I'm in for it. By the way, we have a question from the YouTube chat again, and I think this connects well to all of our talks today. So Christy Choflan, I don't exactly know who this user is, but he seems to know us quite well. He says, continual domain learning assumes that your future sessions will be similar to past session, and you want to avoid forgetting. Does that assumption hold? Could the domain adaptation be better? Now, this is a deep one, actually.
I'll take that. I love that question. We think about that question a lot, and it is a fundamental question in the direction of AI around the world, quite honestly. It is the idea of domain adaptation versus domain generalization. And so domain generalization would mean that you're building a model eventually over time that is impervious or resilient to all the possible sources of domain difference. And so that's the holy grail. Domain adaptation is maybe a recognition that maybe we can't do that, and so therefore we need to adapt to the new system. We have not yet tested over very long periods of time this idea of context-informed incremental learning, but we have been able to see that the nature by which it worked, we can create multiple modes. And so sort of in the old school machine learning sense, we're forcing everything to be into one mode for each of the classes. We can allow it, as I said earlier, to populate multiple different locations. And so the hope would be that if you continue to do over time, you know, as a new day comes and something slightly different, it starts to fit into the mold of what you have. But the power of the context-informed incremental learning is, you know, if we instrument it in the wild, so to speak, so whatever device you're using, if we can figure out strategies to maintain context, whether that's through computer vision or some other option to see what's happening, it can just continuously adapt. It doesn't have to only be during a training session. So we have yet to do that work, and it will require a little bit more engineering to sort of instrument the environment, but that's what we're starting to look at.
I'd add, taking up again this user's question, you want to avoid forgetting. I'm not sure we want to avoid forgetting. Possibly we want a model which will stay up to date to the past week of the signals, so that what the user did in the beginning when he was learning from scratch should possibly have a smaller weight, less importance than what things that he's doing right now do have. But again, so I also have the same problem. There's too little resources and time to do everything, and this is something I would really like to explore.
Yeah.
Marta Gherardini, do you have any final or further comments about resilience, reliability?
Yeah, maybe I just as a take-home message, I think that it's really interesting also and stimulating that there are a lot of different research lines, different biosignal, different algorithm, different strategies. Maybe one of the greatest challenges to remain the clinical translation of these new technologies and approaches. So the testing in everyday life, because the great achievement would be then that the person actually use it at home every day, and it's really useful. And possibly I think that the solution could come also from merging different paths that now are divided, different strategies and technologies that could merge and probably also be personalized for the single person. So but I think it's really interesting what has been done in the last years, and so there are new and great opportunities.
I also think this nicely reconnects to Marta's study on acceptability and usability. Yeah, I mean, the more we listen to them, the people that need our stuff, the better for them, of course, in the first place, and for us as well, as our machines become more reliable and well, better behaved, I would say. Does anyone want to, we're almost out of time. Does anyone want to make some final remarks? Yeah, if not, then, well, 1 hour 15, that's our usual time. So I'd like to thank the speakers once again. Great webinar, thank you very much. Thanks to all the viewers live on the YouTube and the questions that they asked. And thank you to anyone who will watch this video again. We'll see you for the webinar number 11, which is roughly planned end of May, beginning of June. And if not, then see you all around the world in our places and conferences. Thank you very much. Goodbye.
Thank you.
Thank you.